On, please, and we'll run for another hour, 11:30 to 12:30. So what I'd like to show you now for the next few minutes is how to do the same thing in RJAGs so that you can do this stuff on your Macs. So for that purpose, on the course webpage, I created a file called How to MCMC Sample with RJAGs, and I'm going to grab this entire file and put it into a text file. I guess I could have just copied it, but this won't take very long. Control C that sucker and put it into a notepad, for example. That's funny. Come on. There we go. So, the comment character in R is a sharp or hashtag, as we mentioned before. What I've done is this file can be run in R with no difficulties. There won't be any errors. All of my comments to you about how to do things are, I believe, correctly commented, so it should all run. So, step one, create a new directory. For illustration here, I'm going to call it NB10-JAGs. So let me go ahead and do that in this world here. I'll go down into short courses and our short course and create a new folder called NB10-JAGs. All right. Now, in a text file, write your model in the same way you would for WinBugs, except, as I mentioned before, the first line has to say the word model in front of the left curly brace instead of just the left curly brace. And store that text file in that directory. So here, the way I can do that is I can go back to the course web page and grab that model file and copy it and paste it into another notepad, which again, annoyingly, there we go, can sit here. And now, once again, as I said, I use exactly the same model file, except I put the word model right there. And now I'm going to do a save as into that particular folder that I just created. So, okay, short courses, eBay, Google, and NB10-JAGs. And I'm going to call it whatever I said in that other file I was going to call it. So, NB10-model-1.txt, is that what it's called? Okay, so let's go back here. Let me confirm that. Yeah, or actually I can confirm it in my text file, other text file, can't I? So, yeah, NB10- as you say, -model-1.txt. So let's go back here and do that save as and put it where it belongs. Okay, and just to check now, if I go into that folder, that's there. That's good. And that's the only thing you need external to R in Mr. Martin Plummer's world. And to show you for clarity, this function looks like that, except without the sharp signs, of course. Now, open up an R session. Here's one now that's brand new. And change directory to this place that you just put the model file in. So I'll change directory to C, and then down to short courses, and then down to our short course, and then down to NB10-JAGs. Okay, good. Now, if you've not already installed this program, if this is your first time using RJAGs, you have to install it and then load it. Otherwise, if it's already installed, you just have to load it now. And of course, you have to be connected to the internet for this next step to work, because we're going to go out over the internet to grab it. So to install RJAGs, select Packages and choose the Install Packages option. And what will come up is a little window that asks you which of the various mirror sites the CRAN people keep active you want to use. And I generally scroll down to the bottom and I use either USA California 1 or USA California 2. One of them is Berkeley, the other one's UCLA. I never remember which. So let's pick California 1 and hit OK. And now, that's interesting. Already it pops up, or maybe it did that already in my other window as well. Yes, a new window called Packages will pop up. And now what we want to do is to scroll down and find RJAGs. And hit OK. In this case, it's probably going to say it's already been installed in my computer, because it already is. But let's find out what happens when it does. Well, actually, it's happy. It goes ahead and installs it anyway, even though it was already there. All right, so it mumbles a little bit at you with the stuff you don't really need to look at, and eventually it tells you where the downloaded binary packages are if you care, and gives you back the R prompt, the little greater than sign. So everything's fine. That's the install part. Now to load it, now that it's been installed, in your R session you go back up to Packages and click on Load Package, and you get a little Select One window, and these are all the packages I've already downloaded, and so I pick RJAGs and hit OK. And now it loads them, and it mumbles a little bit more, and then it might give you a warning. In this case, it's warning me that the package was built under a version of R that is older than the one that I'm using here, but that's not going to be a problem. So now we're ready to do some work. I don't need that file to be open anymore. So now we have a model file sitting outside of R. We now need to load the data file into R, and the data file is exactly the same as in WinBugs. Namely, it consists of all this stuff that I've highlighted right here. You may recall that's exactly the data file in the NB10 example, except that what you do is you assign it to an object in your current R session. So for illustration here, I assign it to an object called nb10.data.1 by running this code now inside R. So I run this code inside R. And if I do an ls to see what's in my directory so far, that's the only object that's there. And if I type in to see what it is, nb10.data.1, it says, it tells you that it's a list by saying, well, okay, it has elements. One of them is called nb10.data.1 $y, and that's part of it. And the other part of the list is nb10.data.1 $n. And so that comes from this structure up here, list open parenthesis, and then I define an object y equal to some stuff, comma, n equals something else. And so that tells R that you want nb10.data.1 to be a list object having two components to the list, namely y and n. And so if I wanted to access the y element of that, I have to actually type nb10.data.1 $y, and that gets me access to the vector of 100 numbers. That's the data set. Okay, same idea about your initial values file. It's exactly the same as in WinBugs. You'll recognize perhaps that this was exactly the initial values file we had before. Except that, again, you have to assign it to an object in your current R session. So here I'm going to assign it to a thing called nb10.inits.1. So I paste that into my R session. And now we have, as far as Martin Plummer's concerned, we have defined the model file, or we built the model file external to R. We've defined the data file. We've defined the initial values file. Now you do the model checking and compiling, but you do it inside R now. You're not using WinBugs anymore. You use the following command. There's a function inside the RJAGs package called jags.model. And in that, I have to tell it where the file is with the model. And so I say file equals, and I mention it, And by not putting any prefix there, like in the Windows world, you would have to say C:// and tell it the whole path. If I don't tell it the rest of the path, it assumes that this file is in the same directory where the R session is being run in. And you remember I changed directory to that place now. So this command should work now and bring in the model file correctly. And it will then try to essentially rationalize that with the data file, and I have to name the data object I just created and rationalize all that with the initial values file as well. So let's try. I Control-C that guy and come into R and go Control-V. And in a pretty fast, pretty small period of time, Martin Plummer's code says, all right, I'm compiling the model graph and resolving undeclared variables and allocating nodes to the graph, and it says that the graph has 113 nodes in it. And that's because 100 of them are the Y values, and the other 13 are the various things that we needed to define in order to build the model. Now, a strange thing about his code is that it leaves a blinking red cursor on the screen in such a way that the first time I ran it, I thought that meant he wasn't done yet. But actually, if you go in and just type something like 1 right now, he's waiting for you to go ahead and do new stuff. It's just that his blinking red cursor is there to make you think he isn't ready for you to do new stuff. So ignore the blinking red cursor. And as soon as he says he's done with something, he really is. So now I can go back. Now the model's been initialized. I'm going to set the random seed before I do any random stuff. So I'll Control-C that guy and bring it in. I just generate typical sort of large integer as a way to set a seed. In this case here, if you look at the string of numbers at the top of your screen, I generated that one by starting at the 6 and going 1 unit to the left and then 1 unit to the right and then 1 unit to the left and 1 unit to the right. And anyway, you make a big integer, right? So, all right, that's my seed. And now I do a burn-in of 1,000 iterations for the following commands. I assign n.burn-in the value of 1,000, and I run his command inside rjags called update. And it says update the rjags object called nb10.run.1, which we created by running jags.model and putting that into that object there. Update that object with a number of iterations equal to my n.burn-in. And so this is going to go pretty fast, because I only have 1,000. And you remember that it only took less than 1 second in WinBugs to do that, and it took about the same for Mr. Plummer. And now I'm ready to do a monitoring run of, let's say, 100,000 iterations. And this takes longer in Mr. Plummer's world than it did in the WinBugs world. My machine has pretty decent gigahertz, although only 1 CPU at a time. And at that particular gigahertz, it took about 90 seconds, and we saw it only took about 15 seconds in WinBugs. So there might be something that I could do to make things run faster in Mr. Plummer's world. But you see what happens is he creates this little thing in which he adds the stars according to what percentage of the monitoring run you've already finished, and he puts a little percent over here on the right that gets updated all the time to show you how his progress goes. And in the Windows world, you get that little circling object that flashes at you to show you that it won't accept any more input at the screen. It's actually working hard on your behalf right now. So we have another minute or so before Mr. Plummer's code finishes doing the monitoring. Does anybody have a question or comment they might like to pipe up with now?
Have a JAX like a standalone version as well, right?
Yes, there is a standalone version as well. I did not try to show you that because I would have shown you the Windows standalone version of JAGS on this Windows machine. As an alternative to this, you could download the standalone version of JAGS for your Mac OS X environment and run it in that environment. And presumably the steps to do that are similar to the ones I'm showing you here.
Yeah, I tried that. More or less it's the same, just that it's a little bit syntactically, I think we're more closer to R.
What I like about this environment is that now that we're in R, we have the MCMC data set in R, and we can do our own post-processing of the MCMC data set in R. So the things that you saw WinBugs do with pull-downs, I can do them quite easily in R, and I'm going to show you the code for that. In fact, I can do stuff readily in here that you don't get from WinBugs. So it's done, and I think if we'd been counting, it took about 90 seconds. So now let's see what we've got. And now we have some fun. We get to summarize the posterior now. It's been put into an object called nb10.run. Let's see, did I run that yet? Let me see. Yes, I ran that. I should have told you what the syntax is here. You're using the function called jags.samples, and you're applying it to that object that was previously the compiled model, and then you have to give it a vector of variable names that you're interested in compiling. This is sort of like telling it which nodes you want to monitor in the graph, and then you tell it how many iterations there are. So if we looked at nb10.run.1.results, it should be a list object with the components $mu and so on in it. So let's try that. If I come back here and type that and say $mu, and maybe I'll just ask for the first 100 elements to keep it from having to really fill up my screen. So yeah, so it's a list object now, and so I just mention the object that I stored the results in and go $ and name whichever variable I'm interested in, and then I have full access to all those values. Okay. So the first thing I find it natural to do is to pull out each of those columns of the MCMC data set and stick them into their own individual variables. So we'll have a variable called mu.star, which is the draws for mu, and similarly for the other guys. So let's go ahead and run that code first. And now I've written you a set of functions that helps you construct graphical and numerical summaries of each monitored quantity. Someone mentioned to me a minute ago that there's already a package in R you can download called MCMC plots that probably does much of what I'm about to show you now, but I've created the code here, and so we might as well look at mine. So this command here is an example of one of the most complicated commands to learn about in R. The plotting environment in R is almost infinitely adaptable, adjustable. And most of the major adjustments are made with this command called par, which is short for parameters in the plotting environment, essentially, something like that. And so, yeah, basically it sets or queries graphical parameters. And you start looking at it, you'll see that it goes on and on and on. There's so many different things you can do to make your pictures very specialized and so on. But an extremely common one is the one I'm using here, which is to force the plotting window to break itself down into subplots in a little matrix with 2 rows and 2 columns. So I say mf row equals c 2, 2, and that will force it to create the 4 parts of this thing that I call the MCMC4 plot. So let's go ahead and do that first. We'll go ahead and set things up and plot that guy, and it takes a little moment to do that. But now this, of course, is just the same time series plot that you saw in the history command out of the WinBugs world. And again, to the extent that it's possible, you can look at that and see if it looks like there's some sort of problems with it having trend or pattern indicating that it's not in equilibrium. And then the next one is I tend next to plot the density. So I get the marginal posterior distribution as the second plot in the MCMC4 plot. And so there's my marginal posterior, which looks quite a lot like the one we saw in the WinBugs world. And then I'm going to put in some stuff that helps me figure out about what the right Monte Carlo standard error is. And so there are 2 commands in R that help you work with the autocorrelation function. One of them is called ACF, and the other one is called PACF, which stands for partial autocorrelation function. And I'll run them both now, and we'll look at the pictures, and I'll try to explain to you what they mean. So the other 2 plots are created down here. The lower left-hand plot is the autocorrelation function, which again is something that you saw in the WinBugs environment. And this is something, the PACF is something that's not in the WinBugs environment. The partial autocorrelation function is useful for diagnosing the nature of the time series that we're working with here. I can most readily tell you what's going on here by writing something out over here. So let's see what page we're up to so far today. Looks like page 13. A common class of time series models, and this is from work of these guys called George Box and Willem Jenkins in something called the time domain. You can either analyze time series in what's called the time domain, in which you're actually trying to see how the series depends upon itself at various lags going back into the past. So time is indexed by the lags. Or you can analyze time series in what's called the frequency domain, in which you try to approximate a time series with a Fourier expansion and look at the Fourier expansion to see what's going on. And so this is a time domain example. Common class of time series models is called autoregressive. AR for short, autoregressive models of order M, let's say. And the way it works is your time series at time t is thought to depend upon itself back in the past in a regression sort of way. So you regress the series at time t on itself at time t plus t minus 1 and itself at time t minus 2 and so on down to itself at time t minus m. And the way you make it a regression is there might or might not be an intercept term. It may not be necessary, but there's certainly a slope term here. So we could call this slope alpha 1 times that plus alpha 2 times that plus dot, 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 plus alpha m times that. Plus white noise term plus e sub t, where the white noise is supposed to be, the usual thing is to pretend that it's IID normal. It means 0 and some variance sigma squared. And so you can see why these are called autoregressive models, because you're running a regression of the time series on itself. So that's why it's a regression model, and that's also why it's an autoregression model, because you're running the regression on versions of itself that are back into the past. And here's a fact, basic fact. Many columns in MCMC data sets look like AR1. So this means AR of order 1 look like AR1 time series with what people call, well, we know this already, with first order autocorrelation row 1. So we have this general class of autoregressive models of order up to m, in which the series might depend on itself all the way back to m lags, where m could be a number like 5 or 10. But it turns out that there's a natural reason for this coming out of the Markovian character of the chain. Many columns, maybe even most columns in MCMC data sets look a lot like AR1 time series with first order autocorrelation rho sub 1. If rho sub 1 equals 0, then that's a white noise series, white noise or IID series, because that's essentially like an AR0, which is no dependence on the past at all. And the reason I bring this up is that the partial autocorrelation function provides a perfect diagnostic for whether the series behaves like an AR1 or an AR2 or something else. If the series behaves like an AR1, then the PACF plot was going to look just like that. And what I mean by that is it will have a spike at lag 1, which is not numbered here. The lags are even numbers for some reason. But there's a spike at lag 1, and all the other spikes are negligible. And so that's a diagnostic plot to tell you whether you have an AR1 series or not. And if it looks like that, namely a non-negligible spike at lag 1, and then all negligible spikes after that, then you have an AR1. And another way to confirm that is to look at the autocorrelation function, because the autocorrelation function of an AR1 looks like a geometric decay. So we see that the first order autocorrelation here is around 0.25, the same number that we noticed in the WinBugs output. And the second one is going to be on the order of 0.25 squared, which is a pretty small number, and then all the rest of them are quite small. So I use these plots diagnostically to see whether I have an AR1 style time series in that particular column of the MCMC dataset. And the reason I do that is that if that particular column behaves like an AR1, then there's a simple formula that I'm about to show you that works out the Monte Carlo standard error of the sample mean of those draws. And so that's how some of you asked, how did WinBugs get that Monte Carlo standard error? And the answer is they used a method rather like the one I'm about to show you now. So going back to my narrative here, it says the lower left and right graphs in this are of the MCMC4 plot are plots of the autocorrelation function, ACF for short, and the partial autocorrelation function, PACF for short, for the time series of monitored iterations. If these iterations behave like an autoregressive time series of order 1 with first order autocorrelation rho, I really should have said first order autocorrelation rho.1, often denoted by AR1 open parenthesis rho.1, then A, the PACF will have a single spike of height rho.1 at lag 1 and no other significant spikes. And B, the ACF will exhibit a geometric decay pattern with a spike of height rho 1 at lag 1, a spike of approximate height rho 1 squared at lag 2, and so on. And for the parameter mu here, the one we're looking at, the ACF and PACF plots look perfectly like an AR1 with a first order autocorrelation of about 0.22 roughly. Okay, as I mentioned to you earlier this morning, an MCMC time series with a rho 1 hat value close to 0, which would be equivalent to IID sampling, is said to be mixing well. And here we would definitely say that's true of the mu series. So the MCMC4 plot, it shows you stuff that you like to know. You look at the history of the whole time series, which is interesting for looking at stationarity. You look at the marginal density, which is just what you wanted all along. What's the marginal for this parameter look like? And you look at the ACF and PACF to see if the thing behaves like an AR1, because if it does, then there's a simple formula for how to work out the Monte Carlo standard error. Then I can run this simple command here to get numerical summaries. I can get the mean of that column and the standard deviation of that column, and the 0.025 and 0.975 points of that column to get the left and right endpoints of the 95% interval for the parameter. And so let me run that and see. I should get. In fact, I noticed this morning before I came over. I thought that by running the set.seed command before starting the monitoring in the burn-in and monitoring in Mr. Plummer's software, I thought he would pick the seed up, but apparently he's ignored the seed, because you'll notice that the answers I just got a moment ago are a little different from the ones in my file. So I need to read his documentation a little bit more. He probably has his own function for setting the random number seed. What's that? Okay, good. Thank you. So my attempt to set the random number seed seems not to have worked as far as Mr. Plummer's concerned, but he has an easy way to do it himself. And so what we would conclude on the basis of this is that the block of NB10 metal weighs about 404.3 micrograms below the nominal weight of 10 grams, give or take about 0.47 micrograms. And the 95% interval for that runs from about 403.4 up to about 405.2. So we get out all the summaries we want. Except now I need to tell you about the Monte Carlo standard error. And for that purpose, we need to go back into this file, and I need to go a long way down in it. So this is all stuff that we covered last time. And then we also talked about a little bit about how to use, talked about Gibbs sampling. Actually, I wanted to make a remark about Gibbs sampling. So let's look at the details a little bit of Gibbs sampling in the NB10 T model. The posterior of interest is the joint posterior of mu and sigma squared of nu given the data vector and the background information. Okay. And you remember the way Gibbs sampling works is it says create this thing called the full conditional, which basically says, what do you think you would know about mu if by some magic you also knew sigma squared and nu? So the full conditionals are as follows. The full conditionals are, well, what's the marginal posterior for mu if in addition to the data somehow you knew what the right values of sigma squared and nu were? That's the one for mu. And the one for sigma squared says the same kind of thing. What would your opinion be about sigma squared if somehow you knew what mu and nu were? And then finally, the full conditional for nu would be the same thing, except it would say, what would be your information about nu if somehow you also knew mu and sigma squared and the data? So those are the full conditionals in this model. And if you were trying to write a Gibbs sampler for this particular problem, you'd have to be able to work out the analytic form of each of those things and then figure out a way to sample from each of those guys. And the way the sampling would work is you'd take a draw from this one here first using the most recent values of sigma squared and nu. Then you take a draw from the second one using the most recent values of mu and nu, which would include the value you just got for mu a minute ago. And then finally you take a draw for nu using the most recent values of mu and sigma squared, and that would include both of the two values you just got a second ago, and then you'd go back around again. That's how you do Gibbs sampling. This is an example of a general class of methods, example of methods called stochastic relaxation. Because what you're doing is you're temporarily pretending you know something in order to learn about something else. You're relaxing the fact that all three are unknown in a stochastic way by sampling from the thing that you're thinking of as unknown, temporarily pretending the other ones are known. I actually have an experience from earlier in my life that provides an anecdote for what's going on here. My 8th grade geometry teacher was a wonderful person named Mrs. Page. I grew up in the Maryland suburbs of Washington, D.C., and Mrs. Page was from East Texas, which is a very exotic person to someone who's only lived in Maryland for his whole life up to that point. She spoke with an East Texas drawl, which I will not attempt to imitate here. If any of you are from East Texas or know anybody who's from East Texas, it sounds different from Central Texas. It sounds different from West Texas. I mean, it's a distinct thing of itself, and I can't get at it. I lived in North Carolina for a while, and every now and then I can capture that one okay, but I can't get her East Texas anymore. I've forgotten it. But she was a wonder. I went to an ordinary public school in Maryland, suburb of Washington, D.C., where the school had pretty good teachers and pretty good access to materials. They tracked us. Do they still use tracking in elementary and junior high school and high school now, where they try to figure out what sort of rough percentile are you in, and they run parallel classes, and the people who are in the top get one class, and the people who are in the middle get another class, and so on. And so, being in this geometry class already, I'd been tracked into the upper echelon, at least as far as math went, and I think the other things too. And so she knew we were all pretty sharp. We were supposed to be all pretty sharp. And the book that the county gave us for learning geometry out of wasn't very good. And so here's what she did. She pretended to use the book all year long, and we did use it every now and then. But what she really did was she taught us out of Euclid's Elements. She made us prove things from Euclid's Elements. So we actually went back 2,000 years to Euclid, and we worked through the books of Euclid's Elements. And she was basically teaching us how to prove things, teaching us how to figure out how to get from A to B in a mathematical sense, and it was really wonderful. So she would send us to the board all the time, and you'd be all alone by yourself on the board with everybody else watching, and then she would say, okay, here's something I need you to prove, because Euclid figured out how to prove it 2,000 years ago. You should be able to figure out how to prove it too. And she'd say, here's the if, and here's the then, and now go to it, young man. And you can imagine that we were all pretty fumbly at this process, and we would often find ourselves saying things like the following. I don't know, Mrs. Page, I don't know how to prove that right away, but if I knew this, and then I knew this other thing, and then I knew this other thing, then I could show what you want. And she was always filled with excellent East Texas sayings for everything. And so whenever we said something like that, she always would say right away, if we had some ham, we could have ham and eggs. If we had some eggs. That was the East Texas saying for that. And basically, that was stochastic relaxation right there. We temporarily pretend we have ham so that we can learn about eggs, and then we temporarily pretend we have eggs so we can learn about ham. And so that's essentially what's going on, and I didn't realize until many years later that that's essentially what she was trying to say to me through that little slogan. In fact, what's going on inside WinBugs is it's not doing Gibbs sampling in this problem because the full conditional for new is too hard to work with. And so it's actually using Metropolis Hastings sampling here. I need to get back to where I was. I was going to find for you one aspect of the part of this that we haven't covered yet, and then I'll cover the rest of it after lunch. So toward the end, there is a formula. Oh, sorry, yes, thank you. Well, all I'm doing is running a movie that's going so fast no one can read it for the moment until I find the formula I'm looking for. Okay, here we are. So back here at the bottom, page 67, I am showing you the nature of the autoregressive process. Here I'm calling it of order P, but it's just like the thing I showed you a minute ago on paper, and explaining a little bit more about how the partial autocorrelation function works. In effect, what it does is it measures the excess correlation between the series at time t and the series at time t minus k, or equivalently t plus k. If a time series is stationary, you can run time, it will appear the same running time forward as it does running time backwards. And so you can talk about the relationship between lag t and lag t plus k, or between t and t minus k. Anyway, it measures the excess correlation between those two things not accounted for by the autocorrelations. And so whatever's left over helps you instantly to diagnose the order of the process. So like I said, if theta star t is autoregressive of order p, then the PACF at lags 1 through p will be significantly different from 0, and then it'll be close to 0 at all the lags after that. Okay, so we've got an AR1 here. If you've got an AR1, then what's the right formula? And here's a simple formula, it turns out, from time series literature. So suppose that theta t star is a stationary time series with underlying true mean mu sub theta and variance sigma sub theta squared. It can be shown that if theta star t, as t runs from 1 to m, is AR1 with first order autocorrelation rho 1, then in repeated sampling, the uncertainty about mu sub theta on the basis of the sample mean, theta bar star, is quantified by that expression in equation 50 on page 69. And if you look at it, the first part of the thing on the right-hand side is just our old friend sigma squared over how many observations you have. That's the usual variance of repeated sampling variance of a mean. But now we have to do a multiplicative adjustment to that by a factor given by 1 plus rho 1 over 1 minus rho 1. So let's look at the form of that factor. Suppose rho 1 was close to plus 1. and that would indicate not mixing very well in the way I showed you before, then what would that thing in the parentheses be, what kind of value would it have? Would it be big or small or in between if rho 1 got close to 1? You can see it'd be really big because you'd be close to dividing by 0. That thing there is called the variance inflation factor, the VIF, for having worked with an autoregressive series rather than a white noise series. What happens to the thing in parentheses if rho 1 equals 0? It becomes 1. In other words, the formula reduces to what we know is the right answer with IID output. And so the formula makes good sense. It goes to plus infinity as the first order autocorrelation goes to plus 1, meaning that it becomes harder and harder to learn about the parameter you're interested in if there's a really high degree of positive autocorrelation in your Markov chain. Interestingly, what does it do as rho 1 goes to minus 1? It actually goes to 0, and that suggests a way to try to improve on MCMC. If there were a way to change the way you did the sampling to induce a negative autocorrelation between the adjacent values in your series, then you could actually end up getting a smaller degree of uncertainty than if you had made IID sampling, because the variance inflation factor would be less than 1. If rho 1 hat is negative, then that variance inflation factor is less than 1, and you can actually learn about the thing you're interested in at a rate faster than IID. It's possible. And the problem is, I've worked on this myself and published on it. The problem is that it's actually bloody hard to figure out how to create a time series that has an correct MCMC character and yet has a negative autocorrelation. What's a negative autocorrelation look like? Well, if the time series is here right now and it has a negative autocorrelation, what it tends to do is to jump and then jump the other way than it jumped before, and then jump back and then jump the other way than it did before. That's what negative rho 1 less than 0 looks like. And so what you want it to do is to make jumps that have a seesaw character to them almost relentlessly, instead of jumps that fluctuate, sometimes seesaw and sometimes not. And there are some methods for tricking the basic MCMC idea into doing that. It's beyond the scope of what we want to talk about here, but it is possible to do even better than IID. So what this means is now we have a way of constructing a Monte Carlo standard error, because I just take the square root of that expression equation 50 and plug in estimates for the things I don't know, and that tells me what the Monte Carlo standard error is. There it is right there. Oh, thank you. Thus, if you want to use MCMC, boy, that takes a long time, to estimate the posterior mean of a given quantity theta with sufficient accuracy that the standard error of the Monte Carlo mean estimate theta bar star based on a monitoring run of length little m is no larger than some specified tolerance t, and the MCMC output theta star behaves like an AR1 series with first order autocorrelation rho 1, then you would need to get that Monte Carlo standard error formula, which goes sigma hat sub theta over the square root of m times the square root of that variance inflation factor. You would want that quantity to be less than or equal to your tolerance t. So basically what I'm pointing out to you is that expression there to the right-hand side of the equal sign in equation 51, namely sigma hat, and see if I can highlight it in the, yeah, sort of. Sigma hat over the square root of m times the square root of 1 plus rho 1 hat over 1 minus rho 1 hat. That is your Monte Carlo standard error for the mean that's arrived at by just taking the mean of the values in the column that you're looking at in the MCMC data set. And of course, you can solve this backwards now for m and work out that you would need that many draws to get a good idea of what's going on. And in fact, everything about this formula is bad news. It says that the noisier the series you're working with is, that would mean that the sigma would be bigger, and so the more monitoring you'd have to do. The smaller you want your error tolerance, the bigger m has to be, because it's in an inverse relationship in the denominator, and it occurs on the t squared scale, not on the t scale. Similarly here, this is on the sigma squared scale, not on the sigma scale. And then you have this thing here, which goes to plus infinity as rho 1 approaches plus 1. And so everything about this formula is bad news, except that basically if we can figure out a way to sample so that rho 1 hat is only around 0.2, then this variance inflation factor is not that big. And 100,000 draws gives us Monte Carlo standard errors like 0.001 or 0.002, and everybody's happy. So That's essentially how we're going to try to overcome this. How what?
What type is this?
That particular bound, does it work, you mean? Yes, it's a valid formula for describing output from columns, columns in MCMC data sets that do behave like AR1. And so what I do right now in the code here is I calculate it. First I calculate the first order autocorrelation by correlating the series from 1 to its length minus 1 with itself from 2 to its length. That does that thing I showed you before to create the correlation at lag 1. And so that produces the estimated autocorrelation here of about 0.21, at lag 1 anyway. And then I use this formula I just showed you. The Monte Carlo standard error for the mean, estimated by Monte Carlo means, behaves like the standard deviation of that series over the square root of how many draws times the square root of that variance inflation factor. And here it comes out about 0.002. Should be some number like that. Yeah, so essentially I would go back to each of the numbers right here. There's another nice fact about this thing. This formula gives approximately the right order of magnitude for the Monte Carlo standard error, not only of the mean over there on the left, but all 4 of those numbers. So actually all 4 of them are Monte Carlo noisy to the tune of about 0.002 with 100,000 draws. And thus it means you can report, you could report pretty confidently 404.30 if you wanted to. That's pretty tight for the mean. 0.46, around 0.469 plus or minus 0.002, you could report that. 403.38 is pretty solid, and 405.22. Basically, all of those numbers are estimated with Monte Carlo accuracy given roughly by the number I just showed you in this formula for the mean. So returning to my narrative, this is also the right order of magnitude for the MCSE of the other things there. And so I would conclude, as I said, that the true weight is about 404.30 based on this model. And I have to really report to myself and others that all of these results, all these conclusions are conditional on the T model for the data. Always when you're doing statistical calculations, a correct way of summarizing your findings involves a little bit more mathematical hedging than people working with you would like. Your report is always of the form, if I've found a good model for the data, then this is what we should conclude, followed by some work in which you show them that it does appear that we have found a good model for the data. So therefore, this report is worth paying attention to. And I'll give you in a minute, I'll give you some examples of how we might check that informally. And then later in the course, I'll show you some formal methods for checking. So now let's do the same summary for sigma. I'll just go ahead and run all this code as a big block. And we now should have the new MCMC4 plot for sigma and all the results that we had for mu. And so the top 2 things match what we saw in WinBugs, and the bottom 2 things show that this is behaving, sigma is behaving roughly like an AR1 with a first order autocorrelation that's a little bigger than we would like, of about 0.5 or so. It turns out to be about 0.45. And that gives rise to a Monte Carlo standard error that's only a little bit bigger than the one for mu. And so we're able to draw some conclusions about that parameter as you see there in that little block of text. And now let's do the same thing for nu. So I'll grab all of this code here and talk about this stuff. So once again, you recognize the marginal posterior for nu to look just the same as it did inside WinBugs. Here, this is the parameter that's mixing the worst. You can see the first order autocorrelation is about plus 0.6, which was about the same value we were getting in WinBugs. And the autocorrelation function, it looks like a ski slope where it's decaying fairly rapidly. Let me say one more thing about the autocorrelation function. How many lags do I have to go out so that the autocorrelation function goes approximately to 0, looking at this picture? Out around 10 lags, it seems to be pretty small, right? And so some people would look at that picture and say, well, okay, if I was worried about disk space, then a good thing to do would be to thin the series to take out every 10th observation. Because since the autocorrelation function has dropped to 0 at lag 10, that's like saying observation 1 in the MCMC output and observation 11 are pretty uncorrelated with each other, as are 21 and 31 and so on. So if I thinned the chain by taking every 10th observation, that would be a white noise chain on the thinned value. But of course, that doesn't buy you anything new, because it would be a white noise chain that was 10 times shorter. And so, like my English friends say, what you gain in the roundabouts, you lose in the swings, which is something about race cars going around an oval track. You gain in the straightaway and you lose around the curves, right? So you can't make things better by thinning. The only way it makes it better is to reduce your disk space. But you can see by looking at this picture that the right order of thinning is about 10 in this plot by looking at the picture. Okay, and in fact, the Monte Carlo standard error for this parameter is about 3 times bigger than that for the other two, because that autocorrelation is so much larger. And now we get to some pretty interesting stuff for y.new. So I'm going to show you first the MCMC4 plot for y.new. So first, let's look at the ACF and PACF. What do they look like? And AR what? And AR 0. In other words, we appear to be doing IID sampling from the Pasteur predictive distribution. That is correct, and that will always be true in any MCMC that's done in the way that I used the predictive distribution here. Because what you're doing is you're taking a series of draws from the Pasteur to get the parameter vector, and then taking independent draws from the sampling distribution to get the actual predicted value. And the fact that those draws are independent means that this output always has to be IID. So actually, in a Monte Carlo sense, you learn about the predictive faster than any of the other parameters, because it always comes out white noise. But what's the time series plot look like? All of the data values were between around what and what. So let's see. What did we call the data values? They were called, where's the data? NB10.data.1 $y. So let's do a sort on NB10.data.1 $y. All of the data values are between 375 and 437. If the model is good, and it's trying to make a predictive distribution for future values, that predictive distribution should match the actual data distribution pretty well, right? So my first glance at this picture is discouraging, because all the data values are between 375 and 437, and yet some of the predicted values in the sample of 100,000 of them range as low as about what? Under 200, and as high as about what? About 700. So there's some really big numbers there, and really small numbers. That initially worries me. It makes me think that the predictive distribution here is over-dispersed relative to the data. But part of that is that I insisted on getting 100,000 draws from the predictive distribution. Those points are pretty rare if you look at them. The bulk of the observations I was about to prove to you are, in fact, right in that range from 375 to whatever that other number was, 437. But when I first saw this picture, it bothered me, because it looks as though the T model, whenever you allow a T distribution to go down to have degrees of freedom really small, like values near 2, you find that it will every now and then throw out a really, really big outlier, because it's trying to get close to the Cauchy distribution, which has enormous outliers. And the density plot, the scale, the horizontal scale of the density plot is influenced by the outliers there. And so instead of giving us a nice look at the bulk of the y.new distribution, it has run all the way from the lowest to the largest on the horizontal scale, and that makes it look like almost like a point mass, but it isn't really a point mass. It's just been crammed into that little space because of the outliers. So let's see what I wrote here. So I said, first of all, the time series plot for y.new shows that the t-model with small degrees of freedom can generate some simulated predictive data values that are quite far away from the center of the distribution. In fact, farther away from the middle than the actual data values. And so here's a little comparison I made. I got a series of various quantiles of the actual data vector and compared them with the quantiles of the predictive distribution. So that's interesting. Okay, so here I've got the quantiles of the data. The 1% point in the data is about 392, the 5% point about 398, up to the 95% point about 412, and the 99% point about 423. The 1% point in the predictive distribution is a bit smaller than that, 388, and the 99% is a little, actually interesting, a little smaller, is about 420. So actually the central 98% of the distribution fits the actual data values really well. It's just that there's about 0.5% or 1% in each tail where you have these values in the predictive that are much further out than the actual data was expecting. So I'm mentioning to you now, this is a good way to informally check a Bayesian model. You compare the predictive distribution it produces for future data with the actual data values. And if they accord well with each other, then you are actually back in the world of feeling like your model is good. So here I do a QQ plot. I actually do a quantile plot of the data vector against the monitored draws from the predictive. And you might ask yourself, how can R do this? Because there's only 100 numbers in this vector, and there's 100,000 numbers in this vector, but it actually does interpolation. It basically interpolates where would the places be in the vector of length 100,000 if there were only 100 numbers there. It does a kind of interpolation to work out what it should plot. And so what you get when you plot it is that the great bulk of the data, essentially the middle 98% of the data is perfectly fit by the T model. But there's the bottom 1% and the top 1% are wild in the predictive distribution relative to the actual distribution. So what to make of this fact, as I've written here, is a bit unclear. On the one hand, it calls the T model slightly into question, but on the other hand, it suggests that if the T model were right and the NBS people were to make more than 100 weighings, they might get some really outrageously different readings if they actually got more data than that. So here's the numerical summary of the predictive distribution, and I can show you this. I've already mentioned to you that we've got white noise there. Look at the first order autocorrelation is essentially 0. And so the standard error comes out, it's actually quite a bit bigger than all the other standard errors. And that's because we've already learned in the past that prediction is harder to do numerically than inference is. And so we would conclude that according to the T model, future weighings should produce values around 404.3, give or take about 6.5, and that about 95% of those future data values should be between about 392.6 and about 416.0. And I've compared for you here the mean and standard deviation of the data with the mean and standard deviation of the y.new predictive distribution. You can see the standard deviation almost matches perfectly, and the mean is a little bit different. And then finally, I asked R to work out, since this is supposed to be the lower 2.5% point of the predictive distribution, this is the upper 2.5% point, what percent of the data actually lives in the 95% interval according to the predictive distribution? And the answer is exactly 95%. And so I actually feel that all in all, with these informal predictive checks here, all in all, the T model fits the data, the NB10 data, quite well. And if I wanted to analyze this data in the world of Bayesian parametric models, then I would go with the T model with unknown degrees of freedom. It really does seem to capture what's going on. And as I think I mentioned to you a couple times ago, one of the workers at the National Bureau of Standards, Churchill Eisenhardt, a very good statistician, he used to say that real data, when you're doing sequential measurements of something, real data behaves like T on 5 or T on 6 degrees of freedom, something like that. So this is an example where he seems to be right, except it's more like T on 3 degrees of freedom, something even smaller. Anyway, that's it for now. We'll have our lunch, I think, and come back at 1:30. So audiovisual guys, let's turn things off for an hour, and we'll start again right at 1:30.
As you can tell, we have a cafe right outside there.
Yes. sorry. You're listening to it now.
Right, isn't there some theorem or proof that you can do that would show that you never beat IID sampling variance inflation?
No. No, I've actually written samplers that have better Monte Carlo accuracy than IID. And the way you do it is you induce the chain to jump to from one side of the mode of the posterior to the other. You force it to do that. That turns out to be a valid thing to do. But what happens is that you thereby get a greater degree of accuracy in some aspects of the posterior distribution, but a worse degree of accuracy than IID in some others. So maybe in that sense, your theorem is right. It's probably not possible to create a non-IID sampling method that is uniformly better than IID in all ways you could look at it. But I could definitely show you a way to create one that produces estimates of the posterior mean that are sharply better than IID.
I mean, because you could always sample and throw out the ones that don't follow that pattern, but that's not really.
No, that won't get you the correct posterior distribution.
I was going to leave you with this. This is Sue. I actually heard you mention this.
Yes, right.
Here's Trumbo wrote this.
Who did?
Dr. Trumbo.
Chris Trumbo?
Yeah. I wrote this paper on, this is their book, their new book. But
right.
Anyway, this you might want to look at because I thought there's two things that are interesting. Your terminology is completely reversed from what they use on Trumbo.
Interesting.
So the symbols ran it through.
Yeah.
Trying to compare this to yours.
Yes.
But the other thing that I think that they do very well is they talk about the ROC evaluation.
Yes.
Follow right after what you did.
Yes. That would be the thing to look at. And
So they did
the
a
work I
nice
do
job
with the
on
people at
this.
Kaiser, we look at the area under the ROC curve quite a lot. As a way of
So anyway,
so, thank you very much. I look forward to looking through it.
I was just going to say, somebody might have already done all the work for us in terms of routing these things. So there's a package called part3. And it looks like it was developed around the same time RJAGS was. They just wasn't going to
Is it also, it's not Martin Plummer, it's these guys from Japan?
Yeah, but these guys talk with Martin. It looks like they're commit logs.
This guy's from China and this guy's from UCLA, okay, And
So it will already do the parallel.
oh, excellent.
You just call it JAG parallel. I ran 100,000 and I could watch it spawns 4 processes. They're all
Fantastic.
But so if you go this way, and then there's, I think these guys are already built in with JAGs as well, but you can do nice things like, it will give you like nice trace plots with different colors for all the changes.
And so you can look and see if it looks as though they're stationary with the same equilibrium distribution.
Yeah, and then of course you can have it just tell you about the model. It's got a nice print.
Usual sort of DIC
And
stuff.
you can have it saved to a regular bugs model.
Very cool.
Code files.
Could you send me some of that?
Yeah, absolutely.
The only thing I would be worried if it's actually running with on Windows, that should work. We're starting with this on our rack, so when you're doing something in process specific, they should have part of it. Yeah, Windows doesn't support, you know that, right? No, but there is no port within the ARM. Yeah, I think what this is doing. I looked at it, it's actually running.
Are you guys taking another break or anytime soon thing after this? Because we're scheduled to do another paper here. I just want to make sure.
I don't.
Here's our breaks.
Actually, the
Between 2:30 and 2:45 and between 3:45 and 4, those are our 2 breaks. Yeah, between 2:30 and 2:45, and then also, of course, we're breaking for a whole hour right now.
Yeah, I just want to 2:30. Thank you.
Sure.
Professor, anyway, you want to run this on Linux? If you want to parallelize it, I think, running it on some Linux or Unix-based platform.
Yes, and our